I'm Damian Pico, and I'm the project manager for the new Reactor Safety Technology Research and Development Program within the Office of Light Water Reactor Technologies. And this program is tucked under the LWR Sustainability Program, which is managed by Rich Reister, who was speaking just before. Also supporting this solicitation activity is Doug Osborne of the Sandia National Laboratory. The vision of the program basically is to learn as much as we can about the accident at Fukushima, its progression and phenomenology, and apply this understanding and its implications to a research program to further enhance the safety of existing and future reactors. The program goals are to identify opportunities to improve nuclear power plant capability to monitor and manage conditions before and into a severe accident, to improve understanding of severe accident progression and outcomes using existing laboratory models, to inform future future Fukushima Daiichi inspection efforts to optimize data collection and optimize understanding of the actual accident progression, and to review existing laboratory analytical codes to identify and prioritize improvements that can take advantage of the current state-of-the-art in computer modeling. At this point, I'd like to note that the industry is responsible, of course, for the safety of licensed nuclear facilities. So the Department of Energy looks at industry as the primary end users of these R&D products. So we have and we will continue to consult with industry on the scope and priorities for this overall activity. The four technical areas correspond to the program goals. Under accident-tolerant components, the scope is focused on hardware-related issues, including the availability of real-time information under accident conditions, which, of course, was an issue at Fukushima and at TMI, as well as R&D on SSCs that could help prevent or mitigate an accident. The severe accident analysis scope is focused on using existing computer codes and their ability to provide information and knowledge to give us insight on the Fukushima accident phenomenology. This could include some minor upgrades to those codes. The Fukushima reactor forensics scope is focused on providing insight on the active progression through in situ examination of the reactors and also through sampling of the reactors. But this needs to be done on a basis to minimize adverse impact on the D&D activities. And the enhanced safety methods scope is focused on enhancing U.S. safety analysis capability by identifying and prioritizing improvements of existing laboratory analytical codes in support of code enhancements to be performed by our Nuclear Energy Advanced Modeling and Simulation Group. This activity is a little longer term and it needs more user community input and definition. The RC7 task, which is subject of this discussion, falls under the second activity, second focus area, severe accident components. As for statement of need, current accident analysis models of steam-driven reactor core isolation cooling system, or RCIS, are simplistic in nature, making use of table lookups for steam draw and pump flow characteristics that are based on normal operating conditions. The RCI pump requires at least DC power to be available to regulate the water level in the reactor pressure vessel. Otherwise, the reactor pressure vessel can flood, and water will enter the steam lines, and you could have water ingress into the RCI system governor and the RCI system turbine. This has been assumed to disable the turbine. Normally, this means that RCI emergency cooling system is generally considered available for 4 to 8 hours, essentially until exhaustion of the emergency batteries. This behavior was not observed at the Fukushima Daiichi accident. The Unit 2 RCI system operated for about 3 days. The Unit 3 RCI system operated not nearly as long, but it operated well beyond its anticipated failure point. This is believed to be a self-regulating mode of operation or self-regulating mechanism, whereas as the RCI system ran out of power and lost its governor, it continued to operate, and the water level in the reactor pressure vessel rose and eventually flooded the steam line, and you had water and steam carry over water ingress into the RCI system governor and the turbine. But rather than disabling the turbine, which is basically modeled in our assumptions about emergency procedures, the pump continued to operate at a slower rate. It was presumably lugging with water or something was happening, But rather than failing, it just slowed down. So as the RIXI system slowed down, the RPV water level dropped again, and eventually the steam lines cleared, and you returned to an operational mode where you had steam, pure steam going through the RIXI system rather than some sort of two-phase flow, which increased the operational speed of the pump, which raised the water level inside the RPV, and you got back into a two-phase flooding condition in the RIXI system again. So in this system, it's believed, in this scenario, it's believed what was happening is the RIXI systems went over into a sort of a self-regulating mode of operation where it would oscillate between these two different modes of operation and could continue to operate for an indeterminate period of time. The importance of this is the assumption of pump failure at 4 hours, or basically on the loss of DC power, effectively rules out planning for extended pump operability under emergency conditions and could limit operator options to recover from near-accident conditions. Research is sought in novel technologies to develop a thermodynamically based analytical model of RIXI operation with mechanistic accounting of liquid water carryover and pump performance degradation to be done with a multi-phase flow code. Effects of operator action should be included. Fukushima Unit 2 accident reconstruction and uncertainty analysis data will be provided and should be used as the basis for benchmarking of this multi-phase flow model. The multi-phase flow model must be able to show RIXI turbine performance during the Fukushima Unit 2 accident progression. The model must also be compared with multi-phase flow experiments. Additionally, the DOE is going to need some level of confidence that the model chosen is valid for these operating conditions. An initial survey of currently available codes with respect to multi-phase flow and turbomachinery will be required. For the selected multi-phase flow code, a thorough understanding of the code's documentation, such as the exact understanding of what equations are being solved and what assumptions and closure rules are being applied, will be needed. Also, a code result comparison to multi-phase flow experiments that are documented in literature will be required. Basically, we need some sort of a reality check or a benchmark against the results. The drive turbine of a RIXI system is an impulse-type turbine, and the specific geometry of the turbine, for these systems, it's a Terry turbine, and its speed governor need to be carefully addressed in the analysis. The ingress of water into a governor into the turbine is not by design, and its implications are not understood. As an example, the application of a multi-phase flow code, such as RELAB 5 or TRACE, could possibly be used in combination with a CFD code to address the ingress of liquid water and steam into the speed governor and drive turbine of the RIXI pump, and also the potential flashing of liquid. I would note that the impact of liquid ingress on pumping performance need to be characterized, and that the flashing of the liquid into steam could be a significant influence on performance. Basic turbine theory and the understanding of two-phase flow as it passes through the RIXI turbine governor will be key to understanding accident conditions, operations, and additional modeling of turbine exhaust, gland seal drains, and geometry of components, including the governor, should be considered. The schematics and design of a representative RIXI pump, like the one shown in the photograph, will be provided. As previously stated, the Fukushima Unit 2 reconstruction and uncertainty analysis data will be provided and shall be used as a basis for benchmarking of this multi-phase flow model. I would note that there is a consensus that water was being introduced into the RIXI system in the Fukushima Unit 2 accident, but it's not understood if the water actually was hitting the turbines or if it was flashing to steam in the governor or in the turbine housing before it got to the turbines. So that concludes my remarks, and I'll take questions.
David, you mentioned the data available. Where will that be available?
There's a We received a question. I'd mentioned that data will be made available. Where is that data available? The DOE completed, through a couple of our labs, MELCOR analysis of the Unit 2 accident and others, and that was published in August of 2012. And currently, there is an uncertainty analysis to revisit these results and to examine, to explore some of the uncertainties and find out which uncertainties in this analysis were significant, had a significant impact, or could have a significant impact on the results as you varied some of these parameters, or whether they were not particularly consequential. That study is underway and will be published later this fiscal year.
Does the RC7 scope allow for experiment on flow regimes and RIC-C turbines?
This was anticipated to be a computer effort. On the other hand, there will be a particular cost ceiling associated with this, and I wouldn't preclude some experimentation, but we're not soliciting experimental data here. We're soliciting a computer analysis. I'm not sure that answers the question. I'd be happy to revisit that.
The next question is the data available at the proposal/pre-application stage or after the award is made?
The data will be available after the proposal stage, although there may be additional data forthcoming. This is constantly, this issue is constantly being revisited, not only by the DOE and our labs, but a number of other entities, and we will provide data that seems relevant.
What is the time frame that DOE expects this task to be completed?
Well, that would be consistent with the normal NEA process. So this would be a 3-year. You mean the duration or the time frame? The duration. This is a 3-year activity.
Yeah, and the question was time frame, so I'm not.
These NEA solicitations will be awarded when?
Next year.
Sometime
Yeah.
next year. Would it be late? So approximately a year from now. So the time frame, initiation a year from now, and this activities would have a 3-year duration.
If the experimental data is available before or during the proposal stage, where can we find that data?
You should contact me or Doug Osborne at Sandia Labs.
Will it be posted somewhere publicly available?
If we make it available to one participant, we have to make it available to all. So we'll either post it or provide it to everybody who's solicited the information.
Okay, that's all the questions. Oh, we have one more. Can we collaborate with Japanese researchers with their matching funds?
Yes, that's a possibility. I'd be hesitant to get into the details, though, because I'm not sure of all of the particulars of the NEA program. But we should certainly provide an additional explanation of that when we document the responses.
The NEUP program allows foreign collaborators, if they're using foreign money, U.S. money cannot go to foreign collaborators.
Okay, any further questions?
I think that's it. Oh, every time I say that, we have another one. Are there ongoing activities in national laboratories on this topic that universities can collaborate with?
There's a number of analyses that are either underway or anticipated at the national laboratories, and the universities could participate in those through the standard laboratory activities. There's nothing precluded, and none of the data here is classified or controlled.
This is Douglas Osborne from Sandia National Laboratories.
Can there be one project or multiple projects awarded in the work scope, I think is what they're asking.
There could be multiple awards. There has been precedent for that in the past, but I wouldn't anticipate that in this case. Doug, I'd like to invite you to make any clarifying remarks based on the questions that we've received, or anything else for that matter.
Yes, this is Douglas Osborne from Sandia National Laboratories. The data that everyone's asking about is Melcor data, and do have some that's currently available, and I can collect that over the next week or so. And everything else that we're working on that we're going to provide with the uncertainty analysis, I can have whatever we're going to provide as results for Unit 2 available hopefully by the proposal time as well.
Are you considering CFD multi-phase codes or only 1D codes like trace?
Doug, why don't you take that one?
We're open to any computational codes. It can be 1D, it can be CFD, it can be something of your own invention, just so long as it meets the requirements that Damien stated earlier with respects to providing some level of confidence to the DOE that your code's going to be able to operate within the accident sequence that we need it to operate in.